name is Chris Lubeck. I'm a senior here at SWOSU majoring in engineering, physics, and math. I'm also the team captain for the SWOSU Rocketdawgs. This year's competition has forced us to work on optimization in all aspects of our rockets, from building to actually launching.
My name is Cody Conrady. I'm a senior engineering physics major and I'm the co-captain of the Rocketdawg team. For the competition this year, we decided to make our rocket as lightweight and compact as possible. We started in the avionics bay and worked our way throughout the rocket. This is our nose cone. It's got an aluminum tip with a carbon fiber base plate, and inside it we have two truly redundant Altus Metrum Easy Minis, along with a Big Red Bee APRS GPS tracking system for the sustainer. We have recovered this nose cone from several successful flights and no damage was done to it.
My name is Ethan Lehman. I'm a sophomore engineering physics major and math major. I'm new to the Rocketdawgs team this year. This is our airframe for the sustainer. It is a 1.75 inch diameter carbon fiber tube from Dragon Plate with a 38mm motor mount. We chose this to be our sustainer airframe since it holds the golf balls in a perfect single stack and is a very lightweight. A 4-foot section weighs about 7 ounces. Our booster is a minimum diameter build made of 54mm fiberglass tubing from Wildman Rocketry. The fins on the booster and the sustainer are cut from 3mm carbon fiber on our Stepcraft CNC router using a water bath.
Here we have our CAD design for our interstage coupler. It consists of 6 different parts. We have a 54mm coupler, a carbon fiber bulk plate, a 54mm body section, 2 carbon fiber centering rings, a 1.8 inch coupler, and a 3D printed transition piece. All these parts will be connected using epoxy or a friction fit. The 54mm coupler and bulk plate will be epoxied into the 54mm body tube section. This coupler is where the electronics will be housed for the booster section. Then the 1.8 inch coupler and 2 centering rings will be epoxied into the 54mm body tube as well. Lastly, the 3D printed transition piece will be snugly fit around the 1.8 inch coupler to ensure we have smooth flow from our 1.8 inch sustainer to our 54mm booster.
My name is Gunnar Snowden. I'm a senior engineering physics and math major. Our sustainer will house 6 golf balls that will be stored between a motor and a bolted bulk plate to ensure they are secure during flight. The sustainer will be brought down by a 24-inch fruity chute, which is rated for 5.2 pounds for 31 feet per second descent rate in the case the sustainer motor doesn't ignite. The booster will have a 30-inch fruity chute. The sustainer will open at apogee, and the parachute will be deployed by use of a cable cutter from apogee components.
For this year's competition, we'll have 2 main setups. The first one will be an Aerotech K700 going to a Loki Research K1127. This setup has a total impulse of about 3,500 Newton seconds and an estimated altitude of 38,000 feet. We hope to score about 75,000 points with this setup. The second setup is for when if the first one completely underperforms what RAS Aero predicts for the altitude. In that case, we'll use an Aerotech L1000 motor and go to the same Loki Research motor in the sustainer. This one has a total impulse of about 4,000 Newton seconds and an altitude of right around 40,000 feet, so we run the risk of going over the altitude cap of the competition. We hope with this setup we could score around 74,000 points.
Each year at the competition, it seems we have one day of good weather and one day of bad weather. This year, we decided to have a backup plan in case there are poor conditions both days. For our backup plan, we will utilize the same sustainer with a different booster. The booster will be the same as the sustainer with 1.75 inch carbon fiber tubing and a 38mm motor mount. This setup will use different motor combinations depending on the altitude cap. Having this contingency will allow us to get a score on the board regardless of the weather.
We have the CAD design for our flyaway rail guides. These are made of 4 3D printed parts and 3 aluminum rods. The 4 3D printed parts will be printed on our Bamboo Labs X1 carbon printer, printed out of their TPU filament. Missing from this design are the springs, as well as the 4 rail buttons from Apogee Components that fit the 1515 rail. The springs will go along the back and allow this clasp mechanism to open when the rocket leaves the rail. This helps with the overall efficiency of the rocket. There is no extra rail buttons or rail guides on the actual airframe that are permanent.